Today we're going to learn about rational numbers. Our objective is to write fractions as decimals and decimals as fractions. The first thing you need to know is that a rational number is a number that can be written as a quotient of two integers, which basically just means it can be a fraction. So in the beginning of this section, they just want you to be able to identify rational numbers, which is just to show the number is rational by putting it as a fraction or a quotient of two integers. So in the first examples, it asks, is 3, -12, and 4 2/3 rational? So if you notice here, what I did was I just took the 3 and put it over 1. Sorry about that. Flip the screen. And that made it a rational number, simply by putting it over 1. In the second one, it's a little bit more trickier because there's a negative number, so it can look two different ways, and both ways are correct. So -12 over 1 is a rational number showing -12, or you can put it 12 over -1. A little bit trickier over here is our mixed number. A rational number isn't going to be shown as a mixed number. It's going to be shown instead as an improper fraction. So all you simply have to do is just change the mixed number to an improper fraction, like we did here in 4 2/3. I changed it to 14/3. The next section wants us to change fractions to decimals, and we all know the famous line, fractions are a division problem. So that's all you need to do is simply to divide your denominator into your numerator, as I did in our examples here. In 5/16, I always draw the bar right off of the denominator, so I remember to leave the 16 out and put the 5 inside the house, because a lot of mistakes here are made just doing that. They put the 5 outside the house and they put the 16 inside because the 5 is smaller. Okay, and when we're changing a fraction to a decimal, our decimals are going to be small. So here, it took a while for us to do it, but we finally did get to a terminating decimal. A terminating decimal means that in the end, it is 0. So what we did was we just divided 16 into 50. Notice here I just brought my decimal up. 3 times 16 was 48. I subtracted and got 2. I brought down a 0. You can keep adding zeros until you finally figure out if it's terminating or if it's going to be a repeating decimal, like in our next example. When I subtracted 16, which was just 1 times 16, I got 4. I brought down another 0, and I did 2 times 16, which was 32, to get 8. When I finally brought down my fourth 0, I ended up with a terminating decimal because 5 times 16 is 80, so I have no remainders left. You're not going to have a remainder when you're changing it to decimals. You keep going until it's terminating or it starts repeating. You keep adding zeros. So in 4/9 here, again, my 9 is outside, my 4 is in the middle. Once I start adding zeros, I have to put a decimal and I bring it up right away. So 4 times 9 gave me 36, subtracted from 40 gave me 4. I brought down another 0 because I can add as many zeros as I want once I put my decimal. 4 times 9 was 36 again. I subtract, I got 4. I noticed then that these 4s are just going to keep repeating. So I put a bar notation over the decimal to show that, and I'm done. In the next section, they want you to do just what we did. They want you to change the fractions to a decimal so that we can compare them more easily. Fractions are very difficult to compare. You want to think of it in the realm of pizza, because if you had a pizza pie and you divide it into 48 little slices and you ate 42 of them, would that be more or less than dividing the pizza into 30 slices and eating 27? It's still one pizza pie. And remember that with a fraction, it's always part of a whole. So even though this fraction here, 42 over 48, has bigger numbers, it does not necessarily mean it's going to be the bigger fraction. So when we divided 42 by 48, I got 0.875. When I divided 27 by 30, and to change it to a decimal, I got 0.9. 0.9 is bigger than 0.875. So therefore 27 over 30 is greater than 42 over 48. So don't always assume just because the numbers are bigger in the fraction that the decimal is going to be bigger. It's much easier to compare decimals than it is fractions. So you want to always take that extra step, change it to a decimal, and then compare when you have decimals. In the end, though, they want you to put it back in fraction form. So 9/10 was 27 over 30ths. So 27 over 30ths is greater than 42 over 48. This would not be a sufficient answer, having 9/10 is greater than 875 thousandths, because they're not asking you to compare these decimals. They're asking you to compare these fractions. So in the end, your final answer should be back in fraction form. Terminating decimals now means that you do get to a 0. So when we're changing a terminating decimal to a fraction, it's pretty simple. Okay? In the next part, we're going to do a repeating decimal, which it's a bit more complicated. But it's very simple. You're going to look to see where your decimal is. So in 3/100ths, this first one here in green, it says that the 3 is in the hundredths place, so the denominator becomes 100. So to change 3/100ths to a fraction, we simply put 3 over 100. In the next example, we have -9 and 4/10, which just means that the -9 stays a whole number and the 4/10 is our fraction. So when you have a decimal like this with a whole number and a decimal part, it's going to become a mixed number when you're done. What you notice here I did was I reduced it. Okay, so make sure if you can reduce it that you do, because a lot of times we'll leave it as -9 and 4/10, but an answer won't be there for that. They're going to show you the reduced fraction of -9 and 2/5. It still stays negative. We just simply changed the 4/10 as a decimal to 4/10 as a fraction and reduced it. So this is where it gets a little bit tricky. Okay, now we have a repeating decimal, which means that we really don't know the value of the decimal. In this example here, we have 7/10, and we know that the 7 repeats. So it could have this many 7s like I'm showing you here. The 7s could go on and on and on across the screen. So in this case, we're going to set up an equation to solve it. So we're just going to say that x is equal to 7/10, which repeats. Right? Now, if I move my decimal over to the next spot, I'm going to have 7 and 7/10, which it's repeating. Moving it over to the next spot is basically multiplying by 10. So whatever I do to one side of my equation, I have to do to the other. So since I multiplied, or really just moved my decimal over one spot, by 10 to get 7 and 7/10, what I'm going to do here is I'm going to change this as well. Okay, so where we have 10x here is simply because I moved the decimal over once. And why I did this was to solve an equation, I need to have something on both sides. Simply having x is equal to 0.7 that repeats, I'm not going to find out what x is. So if I set up another equation that's equivalent to it, it's the same thing, then I can solve for x. So what I'm going to do now is I'm going to subtract these two. So 10x is equal to 7.7 that repeats, and x is equal to 0.7 that repeats as well. What this does is these 7's repeating are going to cross each other out. So I'm going to subtract here 10x minus 1x is 9x, and all I'm left with here is 7. So all of those repeating digits are gone. So when I'm done, I would divide by 9, these cross out, and I would get x is equal to 7/9. This might be a part where you want to pause it and play it again. I'll show you another example similar to this. This is now where two digits are repeated. So 0.8181818181 will keep on going. So again, we don't know the actual value. So we're going to call it x. X is equal to 81 hundredths. That repeats. Now notice here, this is a 100x because I need to move it over two spots in order to account for the two numbers that repeat. When I do that, I have behind my decimal 81 hundredths with our bar notation. Over here I have 81 hundredths with our bar notation for x. So now I know I can set this up and they're going to line up and cancel each other out, which that's my objective, is to get rid of these repeating digits. So here I have 100x, I subtract x, and I get 99x, and I get 81 here because 81 minus 0 is just 81, and these cross themselves out. The 81 with the bar notation, the repeating digits, cross them out. So now you might be saying, wow, 99x is equal to 81. Simple, you do the same thing. You divide both sides by 99. The 99s are going to cross each other out on the left. X is going to be equal to 81 over 99, which then reduces to x is equal to 9/11. This is the most difficult it gets in pre-algebra, where you have two digits that keep repeating. But you do the same thing you did with the one digits. You move the decimal over to make it equal, but different. So here I just moved it over twice to make it equal, but I need to, whatever I do to one side, I moved it over twice, which is 10 to the second or 100. And so I needed to change this x to 100 as well. And then you just subtract the two. So this is our section on rational numbers.